The number e is defined as the value of 1 plus 1 over n to the exponent n approach as n becomes larger. Let's calculate the value of e. And let's go ahead and fill out this table. When n equals 1, this value approaches 2, 2.48832, 2.5937, 2.7048, 2.7169, 2.7181, 2.7182. So note that as x is become larger and larger, as n become larger and larger, the value 1 plus 1 over n to the x over n is approaching 2.72. Okay. The natural exponent is the exponential function. F of x equals e to the x with base e is often referred as the natural exponential function. Let's get the graph of the natural exponential function. State the domain and rank of the graph. So since we have the exponential function, the natural exponential function, like the regular exponential function, f of x equals a to the x. F of x equals e to the x has the domain of negative infinity to infinity and the range from 0 to infinity. So let's take a look at the graph. First, we make the table of the value. And we fill that in. So rounding up, 0, 1, 1 closer to 3, 2 is closer to 7.5. And so here's the exponential graph. Okay. So labeling this. And this is the graph of f of x equal to e to the x. And the domain and range we stated earlier. So the graph of e to the negative x. So this graph here, e to the negative x. So recall the negative exponent, a to the negative x. It is the same as saying a to the negative 1 times x, right? And it's the same as saying 1 over a to the x. So this is the same as saying we're looking at the graph of 1 over e to the x. 1 over e to the x is reflex. So this graph here reflects across the y-axis. So let's take a look at the table of value. Since it reflects across the y-axis, we have so negative 2, negative 1, 0, 1. This is 7.40, 2.72, 1, and 0.367. So negative 2 to 7.5, close to it. Negative 1 to closer to 3. Zero, 1, and 1 is 0.3. So this is the graph of f of x equal 1 over e to the x. Here we have the domain of all real number and the range again of 0 to infinity. So let's take a look at the next graph. Here we compare the graph with the e of x. Here we have shifted to the left by 1. And shifted down by 3. Compared to the graph of f of x equal e to the x. Okay, so shifted down 3. So our horizontal asymptote now is at y equal negative 3. And it shifted to the left by 1 unit. So here are the points. Yeah. So here f of x equal e to the x plus 1 minus 3. So this point right here is negative 1, negative 2. Take a look at the application problem. A 50-gallon barrel is filled completely with pure water. Salt water with concentration of 0.3 pound per gallon is then pumped into the barrel and result in the mixture overflow at the same rate. The amount of salt in the barrel at time t is given by the equation Q of t is equal to 15 times 1 minus e to the negative 0.04 t, where t is measured in minute and Q of t is measured in pound. How much salt is in the barrel after 5 minutes, after 10 minutes? So part A, for t equal 5 minutes, Q of 5 is equal to 15 times 1 minus e to the negative 0.04 times 5. This gives us 2.72 pounds. When t equal 10, Q of 10 is equal to 15 times 1 minus e to the negative 0.04 times 10. That gives us 4.75 pounds. Excuse me, 4.95 pounds of salt that is in the water. Okay. In part B, we want to sketch the graph of Q of t using the graphing calculator. So let's get a graphing calculator. And let's enter the function into the calculator. And so here we have a button e, second e to the x, negative 0.04 times x. And that is our equation. So let's go ahead and sketch this graph. So what happened when the value of t become larger? What would we expect? So let's take a look. Let's zoom it out. Let's see. Okay, let's zoom it out some more. So here we can see that the value of as t become larger, the amount of salt in the barrel is getting more and more, but it's leveling now. Okay. So see, as t getting larger, Q of t is getting larger and then leveling now. Okay, and where does it level out? So let's take a look at it. Let's do a little tray on our graph. When x becomes larger and larger, let's calculate in this. We should trace in this, and we should have it tray on the graph. When x gets larger and larger, they keep going, and here we keep on going. And keep on going. As you can see, at x larger and larger, the value of y is getting closer and closer to 15, and that was it. It's just getting closer and closer to the 15 and didn't get any bigger. Okay, so here we can say that Q of t is approaching 15. So this here, y equal 15, is the horizontal asymptote of the graph. So let's go back and just take a look at the equation, see what would happen. Okay, so here Q of t, what actually happened, equal 15 times 1 minus e to the negative 0.04t. Okay, because of the negative exponent, I can rewrite this as 15 times 1 minus times 1 minus 1 divided by e to the 0.04t. Note that as t getting larger, the exponent, the e to the 0.4 times t, this one right here, the denominator is getting large. Getting larger as t approaches infinity. So 1 divided by a big number is closer to 0. So this here is getting closer to 0. So 1 minus the number that's close to 0 doesn't really make much difference. So this whole thing effectively is about 1. Okay, so then 15 times 1 is 15. Let's take a look at the continuous compound interest. Here we are given this formula. Let's take a look at this problem. If 8,000 is invested in an account for which the interest is compound continuously, find the amount of investment at the end of 12 years for 3% and 4.5% interest rate. Okay. So the amount of interest in the first part for 12 years for 3%. So in part A, we're given t equal 12 and r equals 0.03. So then a of 12 is equal to 8,000 times e to the 0.03 times 12, and that is 11,466 and 64 cents. Okay. Part P, for t equal 12 and r equals 0.045, 8 of 12 equal 8,000 times e to the 0.045 times 12, and that is 13,728 and 5 cents. So the next question is, which of the given interest rate and compounding periods would provide a better investment? Say if you invest at 5.5 and 1/8% per year compound semi-annually, and 5% a year compound continuously, which one will give you a better investment? So semi-annually, so the formula for this is 8 of t is equal to principal times 1 plus r over n to the nt. The compound interest 8 of t is equal to p times e to the rt. So let's calculate. We want to compare the interest rate compounding period will give better investment. So let's try this. So part A, r equal to 518, and that is 41 over 8, and that is about 5.125%. So then 8 of t in this case is equal to the principal times 1 plus 0.05125, and because it compounds semi-annually, we divide it by 2 times 2 in per year. So let's say in 1 year. Okay, that's t. In part B, 5% per year and compound continuously. So 8 of t is equal to p times e to the 0.05 times t. Okay. So what we want to compare is compare these two values, whether it is larger or smaller. So let's say let's make a table and comparing this. Let's pick the value for t and calculate sum of this. 1 plus 0.05125 divided by 2 to the exponent 2t, and e times 0.05t. Would I compare that? Let's pick the value for t equal 1, 2, 3, and 4 and see what we get. So here we get So we compare these two numbers. Initially in the first year, look like the compound semi-annually, you a better interest rate. But as time go on, as compare all this number, you can see that the compound semi-annually is the better rate.